Good morning, all. Today, we are going to discuss about the module 2, that is all about beneficiation process of iron bearing material. So, during mining of iron ore, whatever the iron ore we mine, that will be undergone the comminution process, that is sizing process, by doing some crushing or grinding operations. And during this comminution process, we end up with a certain amount of fines. So, the end product of the comminution process is you have uh, iron ore in the form of lumps as well as fines. So these lumps we can charge into the blast furnace as a iron bearing feed material. But at the same time, fines whatever are generated, even though they have same amount of metallic value, the Fe metallic, Fe content, but we cannot neither transport it nor we cannot charge it into the blast furnace. Because it's quite difficult to transport the fines because it will be fly away. Another thing is that these fines cannot be charged into the blast furnace because it will create a problem in the permeability of the bed. So at the same time, the fines cannot be discarded as it is having good amount of metallic value. So to utilize these fines, we give some shape to it so that it can be easily transported and also it can be charged into the blast furnace as a feed material. So this is nothing but the agglomeration process. So the ores, whatever we are bringing from the mines, those are called as runoff mines. And the comminution of these ores, it can be done either at the mine site or at the plant site. It depends upon the availability of the resources. So we do sizing technique in multi-stage method, because the total amount of size which is required, the quantity of size which is required for charge as a feed material, the blast furnace cannot be or may not be achieved in the single stage. So, so it can be subjected for primary crushing using jaw crusher to get a size of around 152 mm. And then again, it will be subjected for the secondary crushing, where you use a cone crusher to get a size of around 25 to 55 mm. So after crushing, we do the screening, and the crushing and screening will end up with a certain amount of fines as well as lumps. So we can categorize these lumps and fines based upon its sizes, and accordingly we can use it at different places within the integrated steel plant. So after comminution, the size range of iron ore particles within the range of 10 to 40 mm size can be directly used as a feed material in the blast furnace. And the size range of 5 to 20 size that can be used for the DRI production in coal-based DRI process, and size of around again 10 to 40 size that can be used for the of iron bearing material can be used for the gas-based DRI process. And when it comes to the fines, uh, these fines are again classified into two types. One is coarse fines, other one is very fine fines. The fines which is having a size range of minus 10 and plus 100 mesh, so that is called as coarse fines, and these can be used for the sinter making process. Similarly, we have very fine fines, that is the iron bearing material, anything which is less than minus 100 mesh. So that can be used for the pelletization process. Also, if you see, we have mentioned some size ranges for the iron bearing material because when the smaller size, larger will the surface area, and mm, the greater will be its exposure to the reducing gases, and that will reduce the iron bearing material in a short duration of time. And also the amount of heat which is required for the reduction process takes place also will be comparatively, it will be very less if the particle size is small. So now we will discuss about what are the various agglomeration process which are adopted for the iron bearing material. You see, during the comminution process, enormous amount of fines, around 40 to 50%, fines will be generated. And as I mentioned, that these cannot be charged directly into the blast furnace. So to utilize these fines, we should give some shape to it. That is nothing but the agglomeration process, which is there are various agglomeration processes are there, but predominantly we prefer sintering and pelletization. These are the most successful agglomeration processes which they adopt for iron bearing material as far as the blast furnace iron making is concerned. So start with the sintering. So the term sintering basically denotes the incipient fusion, the localized fusion of iron ore particles at temperatures near their melting point, resulting in the formation of agglomerates. So the objective of sintering is to increase the size of the ore fines to a level which can be acceptable for the blast furnace and form a strong and porous agglomerate. This is very important. If you see the quantity of iron bearing material what we are subjecting into the blast furnace, so around 85 to 90% iron bearing material in the form of agglomerates will go into the blast furnace, and around 10 to 15% will go in the form of lumps. Because these agglomerates, whether sinters or pellets, especially sinters, they have macro pores which you can witness with the naked eye clearly, having very good porosity. And also the pellets are having micropores. So because of this nature, the reducing gases can easily get diffused into these agglomerates and can easily it undergoes reduction process. So the overall kinetics of the reduction of your iron bearing material can happen very fastly. Not only the diffusion of reducing gases, but also after the reduction, the gaseous products also can easily diffuse out from the iron bearing material. So this is one of the reason for preferring the huge quantity of agglomerates as iron bearing material over lump in the blast furnace. And also we prefer agglomerates or sinters to remove the volatiles from the ores and to incorporate flux in the sinters. Yeah. So there's another advantage of using agglomerates is that these agglomerates all are either sinters or pellets are already pre-fluxed products. Good amount of fluxing agent is already incorporated in the iron bearing material. So we no need to add any extra fluxes again as a part of burden inside the blast furnace when you're using agglomerates. And also the heat requirements also can be reduced if you use agglomerates inside the blast furnace, because the endothermic reactions, some of the endothermic reactions which takes place inside the blast furnace can be already done outside the blast furnace while preparation of the agglomerates, especially the CAC or the dissociation and all, which demands an enormous amount of heat. So in this way, the heat consumptions also can be reduced. And on the other side, when I'm saying heat consumption, certainly the coke consumptions also can be reduced. And that will certainly show a great impact on the productivity of the blast furnace. When I'm saying coke consumptions are reducing, means the productivity of the blast furnace is improved. So equipment what we use for the preparation of sinters are white light sintering machine, and the raw materials what we're using for the sintering and its fraction and what is it sizes. If you see, we use around 90% of iron ore fines having a range of 0 to 10 mm, which will be a part of which will accommodate around 60% of the burden. And the fluxes again having a size range of 0 to 3 mm, that is also around 90% of the size of 0 to 3 mm will be used as a part of the burden, and that will constitute around 17% of the burden. Similarly, the coke breeze fuel which we're using, again the size of the coke is also 90% will be of 0 to 3 mm size, and this will constitute around 3 to 4% of the burden. And the rest, if you see, again a small quantity of bleach sand is also used as a source of SiO2 in the sintering process. That is also around 0 to 3 mm size. And apart from this, okay, the iron bearing material which is present in the form of a secondary source can also be used as a part of a burden inside the sintering machine during sintering making process. The BF dust, the flue dust which comes from the blast furnace, flue dust, also constitute a good amount of iron bearing material will be there. So after you subject these off gases for the gas cleaning systems, then certainly you end up with the BF gas, which will be collected at gas cleaning units, and that can be again you can reuse it as a source of secondary iron bearing material. And mill scales from the mills, whatever the oxidized part of the iron in the form of scales. So these mill scales is also a good source of FeO. So this also can be used as a secondary source of iron. Similarly, the as a secondary source of fluxes, we can use LD slag because there is considered a good amount of around 40 to 45% of CaO will be there in that. So that is also can be used as a secondary source of fluxes. And lime dust, that is also used as a secondary source of fluxes. And the sinter returns, the undersized or oversized, the sinters can also be again reused as a part of a burden in the sinter making process. So this is the overall raw material which we basically use for the production of sinters. This is the flow chart of sinter plant. Where whatever the raw material which we discussed till now, these all are collected in separate bins. We have return fines, we have iron ore bin, we have a dolo, we have limestone, we have coke breeze. So all these raw material are collected in the silos, and at required proportion they will be weighed, and it will be transported through the conveyor belt, a common conveyor belt which will be passing below these bins. A weighed amount of these raw materials will be transported through the conveyor belt, and this will go to the pelletizing drum. This is called as MND, MND, that is mixing and nodalizing drum, where this mixture will be undergoing a pelletization process. At this time, we add certain amount of mill scales as well as a certain quantity of water also for proper boiling process. And whatever the product which comes out from this mixing and nodalizing drum, green feed, so that will be allowed to fall onto the sinter bed through the through a silo or a chute, you can say. But before the fresh feed is allowed to fall onto the sinter machine, certain amount of earth, so certain amount of earth layer is formed on the sinter bed initially. On that, this fresh feed is allowed to fall. Okay, so the purpose of this earth layer is to enhance the life of the great bars which are present on the sinter bed. Now this there is a leveling equipment is also there, which allows the bed to maintain a uniform height, a leveler, and then this bed will be moved forward, and it's subject for the ignition process under the ignition hood, where we can use BF gas or coke gas as a fuel, and and here the top layer of your sinter bed will undergo ignition, and it will be further moved towards decombustion chamber. There is a region called pre-combustion chamber, and this pre-combustion chamber is used to maintain the or to minimize the temperature drop occurring when the bed is exposed out from the uh, your ignition hood. When the button is moving from the ignition hood, the top layer will all of a sudden it will expose to the ambient atmosphere, because of which there could be some thermal shock may takes place, because of which there will be some um, fragile formation may takes place in the button. So to avoid that, there will be pre-combustion chamber will be there to maintain that delta T temperature drop. And the heat, whatever we are giving here, basically that will comes from the intercooler. Okay. So we do the suction because here when you are doing red hot sinter will be undergoing cooling process on the intercooler, which moves in a circular motion, and we extract the heat from here, and that heat is basically supplied in the pre-combustion chamber. And from here, the suction basically starts. We have a wind boxes at the bottom part. A series of wind boxes are fixed, where the suction basically takes place, and the heat front and flame front will be traveling across the thickness of the bed, which you can see in this particular picture. Initially, the highest temperature is at the top surface, and as the bed is moving from the ignition hood towards the end of the center bed, the ignition layer is keep on moving layer by layer, and finally, once the bed is moved to the other end of the sintering machine, so the flame the top temperature is reached to the bottommost part, uh, which we call it as a burn through point. And from here, because it is the center bed is a circular moving bed. So when it moves to the bottom side, the entire charge will fall here, where that will be crushed to the center crusher, and the crushed sintered, whatever it is there, that will fall onto the conveyor belt, and from there it will move on to the intercooling machine. And here have the wind boxes are there, and all these wind boxes are collected to one common pipe, and from here that the waste gases will travel through the electrostatic precipitator, and from here it will move out. So the temperature at which the bed is having, that can be read through the thermocouple which is fixed to the wind boxes. And when the moving bed is when the center bed is moving in the downward direction, whatever the sintered product which is stick to the grade bars, that can be fallen down, and that will be collected into the collecting boxes which is present below it, okay. And that can be further recycled. And after the cooling, it will be subjected to the screening operation, and depends upon the sizes we can subject for the various usages. Okay, I'll stop it here, and further process we will discuss in the next class.